Thank you, everyone, for joining Vulkanised, a two-day event for graphic developers to meet up and learn from leading Vulkan experts. Today's moderator is Karen Gebben, CEO of LunarG, who will lead us through the day.
This will be an easy moderated role for me. All I need to do right now is welcome everybody and hand it over to John and Jeremy, who will jump right into their synchronization presentation.
Good morning, I'm Jeremy Gebben, and I'm going to start off this presentation. We're talking about synchronization. And so we're going to go through a review of Vulkan synchronization and some of the new features in the Synchronization 2 extension. And then John Zulauf will go through how Vulkan synchronization works. So I'm Jeremy Gebben. I've been at LunarG for about a year working on validation layers, both for synchronization and general validation. I've worked on GPU drivers for Android at Qualcomm and a variety of other embedded hardware. And I guess we'll get started. So the most important, or the first part to start with on Vulkan synchronization is that most Vulkan commands are started in the order in which they're submitted to a queue, but they can complete in any order and they can run in parallel. Even commands in the same pipeline stage, so two transfer commands, for example. The programmer is responsible for telling Vulkan when two commands have a dependency, and we do this by defining barriers. Now, the spec terminology for a barrier is the synchronization scopes. And the first synchronization scope is what happens before a barrier. It's also the source stage mask is what specifies that in API data structures. And the second synchronization scope is what happens afterwards. We also have memory dependencies. So GPUs have a lot of caches, and different parts of the GPU may have access to the latest version of memory at different times. So Vulkan defines logical access types that correspond to these caches, which might be in each specific GPU design at a specific pipeline stage. Not all GPUs will have every pipeline stage or every cache. And there'll be cache maintenance operations required to make memory accessible to other parts of the GPU or the main memory. So again, we have these access scopes, which are the same idea, but for memory as the execution scopes. So we have the source access mask is what happens is the memory accesses before the barrier. And that's the equivalent of a cache flush or cache clean, depending on your terminology, to get rid of or to make visible what happened before the barrier. And then the second access scope is the memory accesses needed by the commands that happen after the barrier, destination access mask. And this is a cache invalidate. So it makes sure that any stale cache lines are invalidated and removed so that that cache will go back to the next level of memory to find the latest value. So when you don't have barriers, you have a race condition or a hazard. And in this example, we have two copies, one which uses buffer A as the source and one that uses buffer A as the destination. And this is what's called a write after read hazard, because A is involved in both. And if there's no synchronization, something could read A before it's written, and you have no way of knowing if A will contain, at each memory location, and A will contain the old or the new value, and you can get bad effects like tearing or corruption because of this. And the way you fix this is by adding a barrier. So we have a transfer read because we want the read to happen first, and a transfer write as the destination access mask. And then both of these are the pipeline, the transfer stage pipeline, or transfer pipeline stage. So that'll solve that barrier will solve the race condition. And this is something that synchronization validation would catch. There's a whole list of hazards that are detected by validation, which we'll go through later. So then we get to these masks and the pipeline stage and access masks and how they work. So pipeline stages are ordered, and there's a logical ordering defined in the Vulkan spec. It's pretty complicated. What you need to know is that in the source stage of mask, if you set a bit like a fragment shader, that implies all of the previous pipeline stages. So that would block on the vertex shader and anything before the bits you set. And then the destination stage mask, it's the opposite, where it also implies all of the stages that are after whichever bits you set. So you can get away with not listing all the stages that are actually involved in the commands that you're using here. But access masks are a bit different. You need to set all of the bits that you're actually part of the berry that you need. And to do that, you need to have, let's see, so we have a question. The question is, pipeline barriers are the same as memory barriers? Yes. So a pipeline barrier is the VK command pipeline barrier call, and that lets you specify memory barriers, buffer barriers, and image barriers. And we'll go through those in a little bit more detail after this. And then the access mask bits are independent. So there may be multiple bits associated with each pipeline stage. You may not need to actually flush them all or invalidate them all as part of your command. But there's validation that says that you must specify each pipeline stage that's associated with access mask that you want to do, or you'll get errors. So really, you should always try to include all of the pipeline stages and access mask bits that you need explicitly, and not rely on this ordering behavior of the pipeline stages. Some more details about pipeline stages. So in Vulkan 1. Every version of Vulkan before synchronization 2, it was a 32-bit mask, and it's been extended in synchronization 2 to be 64 bits, and that's because we're kind of out of bits to use for new extensions. I think video extension is one of the first that ran into this. And the important thing to know here is that all of the bit values from the 32-bit mask have the same meaning in the 64-bit mask. So you can mix and match without worrying how to translate between the old and the 32-bit and 64-bit mask, as long as you're not using any new bits that are above the 32-bit limit. And the valid values are limited by the capabilities of the queue you're using, which extensions and features you've enabled in your device, and if you're in a render pass or not. So there's special values that don't correspond to a specific pipeline stage or specific piece of hardware. None, top of pipe and bottom pipe, are related to special behavior when you don't want to wait for anything or you want to wait for everything. All commands is also about waiting for everything. So that blocks every single thing. And then all graphics is only the graphics part of the pipeline, so not transfer or compute operations. And then in synchronization 2, several of the stages have been split up, such as transfer has been split into four different stages. Looks like we have a bunch of questions. Let's see, is it still interesting to use the original sync features, or is it recommended to use sync 2 from now on? We'd like you to use sync 2 from now on. It makes the API a little bit easier to use. I'll go through some of that, but synchronization 1 is still supported, and they're compatible such that you can use parts of synchronization 2 with synchronization 1 in an application as you kind of work to translate through. Let's see, what about write hazards and transfer commands when there are two copies into the same buffer? Yes, that's another type of hazard that we'll go over later. And what would happen if you have in that type of hazard is that you might have part of memory with the result from the first write and another part of memory from the second write. And if those are two different values, you might get a mixture that isn't what you wanted. So we'll go through that in more detail later in John's section. So here's an example of the pipeline ordering. And so in the source stage mask, if we set the vertex shader bit, we get all of the gray values. And in the destination stage mask, if we set the vertex bit, we also block all of the green values all the way down to the bottom of the pipe. And one of the important ways that you use the pipeline stages is to form an execution dependency chain. And that's where you have a sequence of 3 commands that have to run in order. And you need 2 barriers splitting those commands up, and those barriers have to match. What that means is that the destination the destination mask of the first barrier must match bits in the destination or in the source mask of the second barrier. So I got a table of what kind of bits related to the ordering that you could use to make a dependency chain. And the best way is to always use the same sets of bits in both the barriers so that it's clear what you're doing. But you can get away with using a later stage or an earlier stage, or using bottom of pipe or all commands. But those effectively idle the GPU. And you usually don't want to do that. Let's see, I've got another question. Do pipeline barriers synchronize only within a command buffer? The effects, let's see, they take place as they execute within the command buffer. Eventually, the effects of all the barriers in your command buffer would become visible with a qsubmit. And then there's other commands like fences and semaphores also will make all of memory visible to outside of the command buffer.
Yeah, the answer is that the effects are cumulative, and that pipeline barriers are used for typically commands within a given queue, not just limited to the command buffer, although pipeline barriers within a render pass only apply inside the render pass. As Jeremy says, it's complicated. However, pipeline barriers are cumulative. As you submit them, they're an effect on how memory is treated. As you use the inter-queue of semaphores and fences, that effect also integrates.
Thank you, John. That's a good answer. So then to get back, let's talk about waiting for everything or nothing. So I mentioned before, we have these special stages. All commands is the first one. And if you put that in your source stage mask, this is waiting for the GPU to be idle before the next command will run. And that is what John likes to call the big hammer, and it will usually kill your performance. Waiting for none, which is a synchronization 2 stage, which is the equivalent of top of pipe, means that the barrier does not wait for any previous stage. So you would really only be synchronizing with the last time the GPU became idle. And so that if you had a barrier with the destination stage of all commands prior to your none barrier, that would form an execution dependency chain, but no other barrier would. And then the destination stage mask, none or bottom of pipe, means that nothing can wait for your barrier. So you'd have to use an all commands source stage mask to form an execution dependency chain. So this is important because fences and semaphores behave this way, and usually that works out okay. And then render pass has implicit subpass dependencies that we'll cover in detail later, because those often don't do what you want. So let's go a little bit more into access mask. Again, this went from 32 bits to 64 bits in synchronization 2, and all the bits are compatible. And then the valid bits are limited by the corresponding stage mask. I hadn't touched on this, that you have to explicitly set all the pipeline stages that correspond to all of the access mask bits you're going to use. And one of my favorite parts of synchronization 2 is that there are individual view IDs that the validation can issue for when the exact error you make here. So if you set the access transfer bit and you didn't say the pipeline stage, set the pipeline stage bit, you would get an explicit view ID saying exactly what you did wrong. And prior to that, you would just get a single view ID that said your access mask doesn't have a pipeline stage and you have to go figure it out. So that, I think, helps validation quite a bit, and hopefully helps developers as well, because we can tell you exactly what happened. There's also a few special values for access masks. None is no memory accesses, and that's a pure execution barrier. Then there's memory read and memory write, which expand to all types of memory accesses allowed by your stage mask. And then in synchronization 2, several pipeline state or access masks get split up, such as shader reads get split up into if it's sampler, storage, or uniform reads. Shader write has an alias that's storage write, and then I think there's some other, the vertex accesses got split up as well. So here's where we get to memory barriers, which somebody asked about. So that important thing to know is that a memory barrier synchronizes all memory accessible by the GPU. There's no ranges or anything like that. You can use it to synchronize your buffers or images unless you need to use image layout transition or queue family ownership transfer, which are special features that require buffer and image handles. And end barriers can be converted to one by ORing all of their masks together. Synchronization 2 moves the source stage mask and destination stage mask to be part of the barrier structure. And this is a convenience feature to let you have one memory barrier to track all of the state associated to whatever operation you're doing, rather than having to supply that as a separate parameter to the pipeline barrier command. So it just makes it a little bit easier to track your the stage masks alongside your access masks. And the implementations in the end will OR all of these together and make a single set of flags that they'll check, or they'll do the operations on. So queue family ownership is an operation that can apply to both buffers and images. Buffer barriers allow you to do that for buffers. It adds the source key family index and the destination key family index. And those are for when you are transferring ownership of a barrier between two queues and you're using the exclusive sharing mode, which means that only one queue family can access that barrier at a time. The concurrent mode is often very slow because it's doing cache coherency potentially between the hardware associated with the two queue families, and that will slow down every single memory access. So usually it's more efficient to just have these barriers to manage the memory accesses when it's actually necessary. So the way these barriers work is very confusing, and there's been changes to the spec about the language about it, and quite a few questions about it, and it took me a while to figure it out. So what happens is you submit a barrier on both the source and destination queues, and on the source barrier only the source access mask is used. On the destination barrier, only the destination access mask is used. But, and this is important, the pipeline stage masks are validated and could potentially be used by implementation on both queues. And so one thing you can run into is that if you're transferring between a graphics and a compute queue or a transfer queue, some of the pipeline stages will only be valid on one side. And so the recommendation is to use none as the pipeline stage on the other queue. And then you also will probably need a, you might also need a semaphore to know when that barrier operation is completed on one queue and when the other queue can start executing. The pipeline barrier part of a queue family ownership transfer is all about memory management and coherency between the two pieces of hardware. And then image barriers are just like buffer barriers. You can do queue family ownership transfer with them. And they also add old and new layouts to allow you to do image layout transitions. And again, these are pretty confusing. And so these will rearrange the memory between different formats depending on what you're doing with that image at any one time, because different parts of the GPU will work more efficiently in different formats. And then the hard part about these is that they happen between the first and second execution scopes of the barrier. So they kind of are this extra thing in the memory model that it's kind of hard to put your finger on sometimes, because they're not their own pipeline stage, and they just happen magically in the background. And the other important part is that each sub-resource of an image can be transitioned independently, which means that applications and validation have to track the current layout of each part of an image, and that can get kind of tricky and expensive. Then synchronization 2 adds some magic layouts that help you transition color, depth, and stencil images without having to keep track of or type if you're doing color, depth, or stencil. So you have a read-only optimal layout that will do the right thing for a color, depth, or stencil buffer, and same with attachment optional. So that just is another quality of life thing where the implementation figures out what you mean based on what type of image it is behind the scenes, and helps you not have to type. Okay, so render pass, and it looks like we have questions about render pass right at the time when we get to it. So I will try to address that as we go through. Let's see, let's talk about this other question first. Why is validation report layout on change when I copy to image transfer issue barrier and do both queue transfer and layout switch within transfer queue? And then, okay, so this looks like a pretty complicated thing that's specific to how validation works. And I would really encourage you to file an issue against the Vulkan validation layers project, and we can try to figure out what's going on. It could be a problem on our side or a problem on your side, but we'll probably be better off trying to solve that through GitHub issues rather than in the presentation. Renders passes and see if I can answer the question here. If I write two subpasses in a render pass and their source stage masks are bottom of pipe and their dest is top of pipe, will the draw commands in subpass 1 be executed after all the commands in subpass 2? I don't remember that off the top of my head. I don't know, John, if you do, can jump in, but we'll kind of talk through how it works. And usually, so in render pass, you're limited to only the graphics pipeline stages. I can't remember if top of pipe and bottom of pipe are even allowed there.
Yeah, yes, they are. Those would be valid execution buffers, but so many other things can go on at a subpass boundary. There could be image layout changes.
Yeah.
There could be other things. Yes, you will have an execution dependency, but that may not be sufficient depending on what else is going on. So yes, that is an execute that if the subsequent source stage mask is bottom of pipe is bottom of pipe, and the final dest stage mask. Wait, are we backwards here? I always have to think about this. So source stage implies everything before, and dest stage implies everything after. So yes, that is an execution barrier between those two subpasses. That is not necessarily a sufficient to handle all conditions because there may be memory dependencies it doesn't handle.
Yep. Okay. Thank you, John. Let's see. We have a question about sharing mode exclusive. With sharing mode exclusive, you don't need to do QFO. That's correct. And just using a normal barrier leads to undefined content of the resource. On desktop, I did some tests and the content was preserved. This might
just because it works doesn't mean it's right.
Yeah, and so desktop GPUs have a very different memory architecture and cache hierarchy than mobile GPUs, and you might be able to get away with many things on a desktop GPU that won't work on mobile because of tiling, the tiling architecture that most mobile GPUs use. Let's see, is there any trade-off when using barriers to synchronize render paths inside of the subtask dependencies? It's an extra command. We'll talk through it. And the implicit subpath dependencies will usually bite you. And so you can usually get away with skipping your barrier and just writing your own external subpath dependency that will do what you needed from the barrier and also be more easier to make correct. So let's go into that. Let's see, so this is the general list of things, and then we'll get to the subpasses in a second. So the load and store operations often cause synchronization errors, especially don't care, which says that you can write, the implementation can write to your buffer even if it's a read. And I think there's a new extension that's making a load op none and a store op none. There's a new load operation type that guarantees it won't write. You also have to be aware of the rasterization order in render paths, which specifies how operations on pixels kind of flow through the pipeline. John mentioned that earlier. That gets rid of the need of some barriers. Pipeline barriers, you have to have a self-dependency where the source and destination subpaths are the same, and then the allowed set of pipelines stages you can use are limited to the graphic stages and the special ones. Usually you're better off sticking with subpath dependencies if you at all possibly can. And then the internal subpath dependencies don't affect the outside world. Again, John mentioned this earlier. The spec says the first and execution scopes only include commands within other subpasses. And then implicit external subpath dependencies don't do what you want. That's my statement. They don't do what I want. So on the left here, we have the implicit dependency, the initial implicit dependency that gets inserted by the implementation if you don't provide your own external dependency. So the problems here are the source stage mask is none, which means that you don't wait for anything to form an execution dependency chain. And the source access mask is none. And then the destination stage mask is all commands, which might be okay. But really, as the question mentioned, you can make this initial dependency into a barrier by changing the source stage mask and the source access mask to line up with what you were doing previously. And that'll more often be correct. It'll make it easier to understand your program because you won't be relying on remembering what this implicit dependency does and how it's written. And on it'll make you more likely to pass synchronization validation as well, honestly. When John first added this to the implementation of sync validation, I found quite a few errors in CTS and many other programs related to these dependencies. And the fix is almost always to make an explicit dependency, and that'll make your program correct, and will work better than adding a barrier usually. And then some other stuff. As I mentioned before, semaphores and fences synchronize all GPU execution and memory. And this is why these, the wait for nothing and block nothing barriers are often okay. So if you end your last barrier with a wait for nothing, then the semaphore or fence will still wait for all the GPU operations before signaling. So that's why you can get away with those wait for nothing sometimes. Queries are the commands that don't, most often don't have barriers. They are defined to execute completely in submission order. So you don't need barriers around them. And then synchronization too, I've kind of gone over the parts of it that are needed to understand validation, but I would really encourage you to look at the VKQ submit to command. It is much easier to use, especially if you're using timeline semaphores. All of the data you need to specify for your timeline semaphore is in one structure rather than split across multiple structures and weird arrays that are hard to get right. And then the new pipeline barrier 2 command uses a dependency info structure, which specifies all the arguments, and that can get rid of a lot of extra typing and potential copy and paste errors in your programs. And then events are redesigned and they're a little bit easier to use. And I guess to emphasize something I said earlier, these 3 bullet points, you can kind of convert over to them one at a time. So you could convert your queue submits and leave your barriers the same and leave your events the same. Or you could convert your pipeline barrier commands and leave everything else the same. The one thing that you have to be really careful with is that the new and old event APIs both use VK event, but they're not compatible. So if you're using synchronization 2 event calls, you have to use them throughout all of the lifecycle of that VK event object. Otherwise, you'll get undefined behavior and validation errors. So that's the end of my section. We've done Q&A on the way. So I have another question coming in. If anyone has any questions before I hand over, we'll go through them. So for subpasses, we should also use pipeline barriers in addition to using top and bottom of pipe, or just the pipeline barriers are sufficient to order them?
I would again say this is where the subpass dependencies come into place, and you want to be as tight as you can be on those, because anytime you throw a big hammer and say wait for everything before and have everything after it wait, then that will happen and you will get greater numbers of stalls. So you should be setting a minimal set within the subpass dependencies of the usages conflict for the usages you have between the subpass barriers. So.
Yep, and if you're using an all commands or top or bottom of pipe barrier that forces a wait for everything, you're leaving performance on the table. That's really, I mean, you should really only be doing that when you're debugging.
All right, Jeremy, you ready to hand it over to me?
Yes, I am. So thanks everyone. That was fun, good questions. And now we'll go over to John.
Hi, I'm John Zulauf. I'll be presenting the next section. I joke that I'm so old, my first Pixel was on a printer. So I'll be talking about how to validate this. So clearly from Jeremy's excellent description, this is difficult and challenging material. So it's important that you're able to check that you've got it correct. So what synchronization validation does is to detect the hazards that Jeremy's been talking about. It does so at byte resolution and for all of the VK command types, and it has Sync2 support in it. However, the current release has some limitations. We only handle hazards within a single command buffer. There is some hazard detection for aliases of the same memory, though it is not complete. Currently, it's only for similar access patterns. I mean, for example, two images that are true aliases are going to correctly report that, or two buffers that are true aliases are going to correctly report that. We don't support byte swizzling in terms of images, and we don't do either GPU assisted or all extensions. And frankly, we can't do assessments of what is the compute shader's access pattern, because we don't simulate that. So let's go over the hazards. Jeremy alluded to them. There's really 5 we look at. The ones you usually think about: read after write, write after read, and write after write. Notice that read after read is not a hazard. It doesn't matter if everybody reads because nothing is changing. However, when you get a read after write, you don't know what you're reading. You don't know if you're getting what the most recent update was or something prior to that update. And you don't know that what you're reading won't change mid-operation. So, for example, the typical presentation of this bug is that I do an image copy, and the resulting image copy is torn, meaning it's got half of one state and half of another state. So that's a read after write. A write after read is I'm still using it and somebody starts updating it, which means the last use of that resource, again, will potentially be torn. It will get either the state I expect, or it'll get the next state that I wasn't expecting. And again, you'll get some of one and some of another. Write after write, if I've got 2 operations that are writing the same addresses in memory, then which one is the final state you can't know, because which one gets retired to memory last is the one that will be the final state. But it could be on deeply pipelined architectures like graphics processors from any set of operations. And then Vulkan specific, these are actually more kind of the general race conditions you think about on a CPU, but they happen specifically in Vulkan between subpasses that don't have any dependencies. So when you look at the subpass dependencies define a directed acyclic graph. There are nodes that are parallel in that graph. They have no lines connecting them. They are free to operate asynchronously. The same thing between 2 queues. When you're submitting to 2 queues, those queues can operate in any order. And if there are no synchronization primitives, then you can't get those operations again happening in any order. And those are writes that happen in an unsynchronized way against other writes, or reads that happen in some unsynchronized way relative to other writes, reads and writes. So the theory of operation inside synchronization validation is we look at the history at each byte. For efficiency, we look at ranges of bytes. We look at the stage and access of the operation. And we only look at the most recent. If you read the white paper that we published earlier this year, it talks a bit about the theory behind most recent access. Effectively, if the logic is, if there's a barrier between my current access and some less recent access, then there was already a hazard between an intervening access and that access with which I would have hazarded. So we can get away with that shortcut, thankfully. We look at how the synchronization applies to the state of the resource. You can think of this as almost byte by byte metadata. How was it used? What synchronization primitives have we applied to it? And then each time we have an operation that affects the state of the memory, then we say, is this valid relative to the previous accesses? We're going to do a live demo, but going into this, should talk to you a bit about how you want to use it. The first thing you want to do is to make sure that you have a clean application relative to all other all other validation. For the first part, synchronization validation isn't doing parameter level validation. It isn't doing a lot of state machine validation. So if you have validation errors that are occurring in parameter validation or core validation, or even in best practices, then it's possible that we're just trying to validate against an invalid command stream, and it's pointless. Also, we do it in isolation because synchronization validation is fairly heavyweight. We don't want to do it at the same time as doing, say, core validation, which with all features on can also be somewhat heavyweight. We can enable it in several ways. This I also point you to the white paper through vkconfig, through the settings and through environment variables. As I said, when we run it, we turn off all other validation options. And I invariably run it in the debugger. The messages are, well, we all know about validation messages. They are detailed, they're long, they're verbose, and sometimes inscrutable. However, the reality is that when you get a hazard, you really want to see where in your code that hazard came from. So run it in the debugger, set a breakpoint, either debug action break or set a breakpoint in one of your debug callbacks. And when you get that error, then you'll be able to go through your call stack and say, what was the access that caused the problem? And so now it's time for a live demo. Hopefully this isn't too much of an eye chart. The project I'm in is actually Vulkan samples. This is unmodified from master of a couple of months ago. And I've set it up the way I set it up. And there are lots of ways to set it up, but the way I happen to set it up was to use the environment. And these environment variables are the same as is listed in the white paper. So I'll reference you to that. And let's go ahead and start the debugger. Now, ironically, I got this and I said, well, let's see if there's a good place where I can inject an error. Well, it turned out that I didn't need to inject an error, that I immediately got an error. And let's take a look at this error message. If I can. So here's one of those errors. Notice that it says we have a write after write. And we're going to go through this error message in detail in just a second. But it tells you we have a write after write hazard. And we can look up the call stack to see where that came from. And we'll come back to this in just a second. So congratulations, it's an error. So we have a write after write where we had an image layout transition that says, oh, there was a write that happened before me. It's important to realize that that layout transitions are full sub-resource read-write accesses. So they have to be treated as if they were a write, and they're validated as if they are a write. So how does synchronization get applied, have validation get applied? We look at all resources touched. We're looking again at ranges of memory, either within a buffer that's been written to a read from, or from an image sub-resource, or even a range of pixels for an attachment. But for each of the resources affected, we do the following thing. We say, what does the current operation do? And this is the stage access that Jeremy was talking about. And not all pairs are valid, not all stages are valid with all access types. And so we synthesized a set of enums, which we report, which are simply all the valid stage access pairs. They reflect the sync2 pipeline stages, and they include the implicit operations that happen in layout transition, load, store, and resolve. The second thing that validation thinks about is what were the prior commands. It looks at that state that we've stored for each range of bytes. What just happened? And then finally, what sync operations happened since that last operation? And did they apply at all? Because when you think of the source and destination access masks, did the prior access exist within one of the source scopes, either the source execution scope or the source access scope? And does the current operation live within either the destination execution scope or the destination execution or access scopes? So once we do that, then we're able to produce one of these validation messages if we say, aha, this isn't safe. And all of them, well, most of them, have the following form. We give the command, we give the hazard type, we give specific information for the command, and then we give information on the access. What is the current access and what are the prior either accesses or synchronization operations? So let's take a look at this in detail. So here's our error message annotated. It was in pipeline barrier. It was a write after write. Here's the image it was in. The debug utilities are there, so you could, in this bracket, actually have a name for this. So debug, if you're not sure what image this is, you can use the debug utils to add labels to your images. The current access, as I said, image layout transitions are full sub-resource read-write accesses. So this is the current resource is an image layout transfer. And the prior usage was a transfer, happened to the transfer stage, and it was a transfer write. So this is probably a copy. And in fact, the prior command was a copy buffer to image. There has been no write barrier since. And these last, okay, there's the current access. There's the previous access, as I said. No barriers. That may give us a hint why we have a problem. This was what the last thing that wrote before this command was. And then this is the sequence number within the current command buffer. And when you're not in the debugger, this is more useful, and this will be more useful in the future as we support multiple command buffers. When did I write this? Which version of this command buffer was it? Within that error message, you'll also get additional details, which are specific to, was it a copy? Was it a draw dispatch? Is this an image barrier? Is this a render pass operation? And those details will also be included in the error messages. All right, let's go back to here. Let's look up the call stack. Let's get out of this, and here's where we are. We're at this, in fact, as we knew we had to be, we're at an image barrier command. Okay.
John, I don't think your screen is switched over.
Ah, let me do that. Can you see my Visual Studio now?
Yep.
Excellent. Thanks, Jeremy. So here we are, as we knew we had to be, at a pipeline barrier command because we're doing an image layout transition, and it said we were in the pipeline barrier command. But if we go up a layer in the Vulkan samples, we'll see that here's the barrier that got constructed. And you'll notice that the source access mask is 0. That means that we aren't going to wait for any accesses prior to this barrier. Well, this barrier wants to do a write. And in fact, you can see above that we just wrote to this image we had a problem with. So here's our write after write in a nutshell. We did a copy buffer to image, which I assume that if I were to click into here, this would be a VK copy buffer to image. To this image of fonts. We didn't even get past the GUI loading. And then we decided, oh, we're going to change the image layout. Well, we didn't wait. And this is the code that exists on master today. Now, obviously, like on any good cooking show, I've pre-cooked. I can go into the oven and pull out my pre-cooked chicken. And here is, in fact, what we needed to do. We needed to wait for a transfer write. Well, given that we knew that our hazard was versus a transfer write, that pretty much told us that's what we needed to do. So if I stop, build, and this is interesting as watching paint dry, I'm sure, and start debugging again, we should get past there, and we get to a new error. Let's take a look at what that message is. This is another write after write, and it's a write after write on a layout transition versus a load operation. So load operations are also writes. This is a clear, it's a write. The layout transition was a write. And if we go up through the code, we will discover that the render pass is not defined with a within this external subpass dependency, because we're in subpass 0, to have a dest access mask that protects that load op clear from the image layout transition. And that's as far as I went, because I figured 2 errors live were good enough. Let's go back. I feel I've either stunned you or put you to sleep. All right, so given that just within, and in fact, it shouldn't surprise anyone that we found errors. We have found synchronization errors in every piece of code we have ever tested the synchronization validation against. So the fact that we find it in Vulkan samples isn't surprising. At one point, I had the last 2 changes to VK Quake because when I said, I need some open source test code to run against, I tested against VK Quake and found errors. When Godot was doing its port to Vulkan in a pre-beta stage, I asked them if I could test against it and found 5 or 6 issues, which got rolled into Godot as fixes. And the Godot people were very, very supportive of that. So again, every time we look at something, we find one. There are AAA titles out there that we've tested against, and we have rolled that information back to the developers when we found it. So, if you're not testing this, you have errors here, guaranteed. The disable and enable, we will, Jeremy, can you answer that? Just type it in or point to the white paper. The disable, you list all the modules you don't want.
Yep.
So here are the frequently found issues. The missing pipeline stages for memory barriers, because the stages are, and this is really common, because pipeline stages are logically extended for synchronization, but not access. You'll get people that assume that, oh, I set a fragment shader stage in the pipeline in the source stage mask, and that means that I've covered for shader access, I've covered the vertex shader access. Well, I haven't, because you have to specifically call out each stage and each access you want a memory dependency on. The spec has improved. We now have error messages for invalid stage access pairs. So people will specify a stage that doesn't have the access they think, or an access that doesn't exist on a stage, so they get no barrier. The implicit sub-pass dependencies in RenderPass effectively do nothing. Unless your RenderPass is effectively doing nothing, don't count on them. And also think about the fact that you probably have image layout transitions going on in your subpass, between subpasses, either from external or to external. The transition to initial state, from initial state to the state of the first subpass, or from the state of the last subpass to the final layout. Those happen, and you need barriers there. Note that you don't need barriers for the things that are raster ordered. For example, you don't need barriers between draw commands to the same attachment because the pipeline takes care of that. Same thing. But when you change between attachment usages, you then do need. And then notice that there are different stages for the load and store operations for depth stencil and for color attachments. So someone will go, well, I've got a barrier for my color attachment stage, so that should be enough. Well, if you're also doing a layout transition or a load for a depth stencil stage and you didn't defend against that, then you're going to get a missing validation there. So how do we attack this? The simplest approach is kind of by inspection. Again, and the folks on the Godot team said I could talk about what I discovered. They have metadata within their application, as most engines or applications have, about how a resource is being used. That when you look at using a barrier, and barriers are almost always needed when you change roles. If you can look at your metadata to say, what was my last role and what is my current role, then you know what your former usage used to be, and you know what your next usage is going to be, which allows you enough information to specify what your source splat masks and your dest splat masks need to be by splat, stage, or access. So that's, the first thing is just look at it. When you get an error message, look at it, says what right barrier does it think that it had versus what hazard did it get? And then go look at how you use that resource. And then of course, the access info will give you more information. Let's say whatever metadata you're tracking within your application is either insufficient or incorrect. Look at what it's telling you, and that allows you to know what you're missing, either in the way you're tracking the usage of your resources within your application or engine, or in terms of how you're setting up the barriers you need. The hazards you get versus prior layout transitions is really looking at the dest stage mask and the dest access mask, because since an image layout transition happens between source and dest, if your hazard is versus a prior image transition, then you've got a missing stage in one of your dest splat masks, where splat is star. I don't know if that's common terminology. And also, if you have a hazard at an image layout transition, then you're missing a stage a stage or access in those masks, because again, it happens after availability and before visibility. So it happens between source and dest. So that can be pretty explicit. Anytime you go between a role from being a write to target and a read from target, those are the places where you're going to see it, and you're going to see that your usage used to be a read usage and now your current usage is a write usage. That tells you what to look for in terms of the role change and how to track how your resources have changed roles. And then finally, and frankly, I've used this in every form of synchronization debugging I've done, whether on CPU or GPU, is the method of bisection. You insert a big hammer barrier. You wait for all commands, all stages, all accesses. That means nothing before, everything before is done before this, and nothing after happens. When you do this, you can localize where the missing real dependency you need to insert lives. If the error disappears, then you know that the missing barrier or usage is before that point. If it doesn't, then you know that the missing barrier is after that point. And you can just keep moving this big hammer until you find it. And I found it a very, very effective method over a large number of years. But don't use it as a crutch. Don't, at the end of the day, say, I am going to just leave this big hammer barrier because I don't have time to fix it, because you're leaving a lot of performance on the table. And then finally, as a reminder, as you change things, make sure you go back and do core and parameter validation so that your changes are also valid. And I know that's a little bit of a pain. The nice thing is that vkconfig can quickly change these things for you. So that's a place where vkconfig can probably help your workflow a lot. But as you make changes, make sure you go back and make sure it's valid. All right, that is the end of my slides. These slides, are all these links in the chat? They should be put in the chat at some point.
Yes, we'll drop them in.
Okay, and are there questions live? I feel like
so there was one question earlier about how we're only tracking this synchronization validation within a single command buffer. And I mentioned that is work in progress to expand that coverage.
That is correct. The current tip of PR in Vulkan validation layers is support for secondary command buffers. That will be our first multi-command buffer support, and then following that will be command buffers within a single queue. And then following that, we're going to want feedback from the user community, because what follows that there are a couple of directions to go, and we'll look for community feedback. We can either swallow the big task and start going for multi-queue, or we can start fleshing out more of the extensions that we didn't cover. We can flesh out things like better aliasing support. Right now it's limited. We can flesh out things like swizzle support. So there are a series of additional directions we can go once we get kind of our first end goal is to have multiple command buffers in a single queue. That will be kind of the end of what we call phase 2 development. What is in phase 3 is going to depend on user feedback. And so please be involved. If you have a favorite feature you want to see, we posted the link to the Vulkan Validation Layers GitHub. And we're on Slack and we're on Reddit.
Let's see, there's another question. Does validation support split barriers, aka barriers via VK event?
Yes, event support was the last feature we added before we considered we had kind of 1.0 functionality in synchronization validation. So yes, we have event support, and that event support is also extended into when we do secondary command buffers. It'll allow events set and wait at the various secondary and primary levels correctly.
let's see. So another question about render paths, which I'll try and answer offline in a second. And then we had someone anonymous ask a question that I'm not sure if I understand correctly, which is any plans on tracking the correct order of synchronization? Which I said, since we're doing this as part of every VK command call, we're detecting errors as soon as they occur, which was my interpretation of how to answer that. But I don't know if the person wants to try to elaborate.
Certainly, we've tried to look at any errors induced by, for example, when we talk about split barriers, we do track the state machine of the event. So if, and in fact, we even look for the race conditions or the undefined behavior when you don't reset relative to set and you don't have the correct synchronization operations in there. So there is some support about that. But I don't know, beyond that, I don't know what the question is looking for. I've never heard 213 people be so quiet. Well, I thank everyone for their attendance. I hope you have learned a lot from Jeremy's presentation. It's an excellent overview of synchronization. And I hope that as you use synchronization more carefully and more efficiently in your application, that you'll get good value out of synchronization validation. One of the things that I didn't say is that as you go from big hammer to smaller hammer synchronization operations for efficiency, synchronization validation can be your friend, because if you say, hey, I don't need this synchronization operation because I want to go faster, well, make sure you run synchronization validation against it so you can have confidence that your leaner, meaner synchronization, which reflects what you learned from Jeremy's presentation, is still correct from the things you learned in my presentation. So again, thank you very much. Jeremy, thank you very much.
Thanks, everyone.
Thank you, John. Thank you, Jeremy.